Donc, mesdames, messieurs, chers élèves, chers étudiants, chers collègues, well, dear colleagues and friends, so welcome to the 32nd edition of Journee Georges de Rham. So I'm sorry a bit for the inconvenience. It's not the speaker's fault, it's just organizer's fault, but we seem to be able to resolve everything. And so we're very happy to welcome you back, we'll have some questions and answers at the end of two talks. So if you want to pose a question, you can scan this QR code and do it in a web form. And there will be aperitif at the end as planned, so everything is as planned. So I want to say a few words about Georges de Rham, because I think there are students and high school students who don't know who he is. So he was one of the central figures in 20th century mathematics, and certainly a central figure in the mathematics in Geneva and Lausanne. This is his thesis defended. So he is Swiss. He defended his thesis in Paris. And if you look closely, you can see that Cartan, Montel, and Julia, of Julia Set's fame, were his rapporteurs. And here are some of the pictures of what he did. So this formula, it kind of looks trivial. It's HP of M is equal to HP of M. Just one has index dr, which stands, you can guess for whom. And the difference is it's like as important as Pythagoras' theorem. Pythagoras' theorem says that algebraic formula a squared plus b squared equal to c squared gives you a circle. So it's equation of circle. So it relates geometry to algebra. So this one relates topology, so just properties of topological space, to properties of analytical functions which exist there. So it relates to very far areas of mathematics. So for example, here there is, it shows that the plane with a puncture is non-trivial topology because there is a vector field around it which is curve-free in plane with a puncture, but it's not a gradient of something. So this is just an example. He also did many other things. For example, he did fractals. He actually was one of the first who draw von Koch snowflake. Von Koch snowflake was drawn by von Koch as a function, not as a set. And besides mathematics, he really enjoyed mountains. And this is a quote we had from 300 years celebration of our section. What is similar about mathematics and mountaineering? That every passage, however difficult, is just a combination of simple steps. And if you figure them out, then everything becomes trivial. Well, the problem is to figure them out. Now this is about de Rham, and it's our first speaker is Raffi Coifman. So we are very happy to have today two great scientists and very good friends of many of us. And usually when we do introductions, you know, people do introductions or wrong way. He won this prize, that prize. You can read that on Wikipedia. They both have many prizes, many accomplishments. So I decided to just tell a few fun facts. Well, the first fun fact that Raffi Coifman, as he's called by friends, is graduate of our university. Hurrah! And this is the proof that as a student he was here in Geneva. Jadot was a little bit lower, so you can judge the time. This his advisor, Jovan Kramata, and he was one of the great Serbian mathematicians who worked half of his life in Belgrade, half of his life in Geneva. He is very well known in analysis. For example, I think he gave the first understandable proof of Hardy-Littlewood maximal function theorem. That was sort of, well, Raffi can tell you at Q&A, he ended more or less randomly in Geneva, but it went out all very well. He went in harmonic analysis. We have the same background. You know, what I admire about Raffi, he's a rare mathematician who did tremendous work both in applied mathematics and in pure mathematics. It's rare. Usually we either do pure or do applied, and he has like two phases, applied phase and the pure phase. And most of his work was on harmonic analysis, so it's basically analysis like not the first. So the first year of analysis, if you are a student, you just use the maximum you get is Cauchy-Schwarz inequality or triangle inequality. So harmonic analysis, when you learn how to make integrals converge when they a priori don't converge. And it also centers a little bit around sine functions of Fourier transform or about wavelets. And Raffi, well, he has many theorems in harmonic analysis. He was one of, I would say, very few central figures in the wavelet revolution which changed the signal processing. Now, who has used Fourier analysis in his life? Raise your hands. Okay. Who has used wavelets in your life? Raise your hands. Okay, well, it is. I never used. I know them. Okay, who has ever made a picture with his mobile phone? Raise your hands. I don't believe you. No, you never made a picture with your mobile phone. So whoever made a picture with his or her mobile phone used harmonic analysis and wavelets. And it's actually surprising how much mathematics is in our everyday gadgets. So then, I got very much to lead to the topic of Rafi's talk. I got very much annoyed when I miscalculate something in the supermarket and people say that, well, you're a mathematician, you should be able to count. And do mathematicians study numbers? Well, normally we study not numbers. We study like shapes, formulas, abstract objects, but sometimes we have numbers. So this is a very famous table of numbers. Who knows what that table is? Wow. No, it's a Rudolphian table. So it's a table which was collected by Tycho Brahe of planetary motion and published by Kepler after Brahe's death. But what we see now when we do these numbers, we see that actually they show that the movement of planets is elliptic and not circular. And then we see Newton's gravitational equation. So what I mean when mathematics study numbers is sometimes you have a sequence numbers from physicists to biologists, and you should order them to see something beautiful behind, which usually will be not a number, but some structure. And that sort of brings me to the, now I'm not very experienced with Max.
Let me do that.
Okay, no, I already did something.
Okay. So, by the way, thank you. I've not been here at the university for 60 years, actually a few years ago. That's different. So the reason I came to this workshop that we have, which is extraordinary, is that 2 years ago, Stas and I discussed a Netflix documentary that was very impressive to him. He told me, go look at it. It was about the octopus. And Octopus, My Teacher. If you haven't seen it, I recommend very strongly that you do, because when you see the whole interaction of the octopus with the photographer that followed him around for a year, you realize that the octopus is really, really intelligent. In fact, it's probably, I don't know, my opinion is it's more intelligent than we are, in the sense that it's completely capable of being in a very challenging situation and finding a response to that situation. And if you know about their life, they don't have any parents that teach them how to beware from various issues in the environment. They sort of learn it on their own. That brings us to machine learning, right? They learn it on their own, and they find original solutions to challenges. Like, for example, if followed by a shark, he goes and hides in the vegetation underwater. If it doesn't work, he jumps on a small outcrop, an island, and nobody can follow him. Or if a crab is there that can chop one of his tentacles, he takes a seashell and uses it as a shield. So we're talking about somebody who was really, really creative. And creative in response to challenges that he may have never seen before. That's amazing. I guarantee you that we don't know how to do that. I mean, we do it because we're trained, we've seen it, we have some experience and so on. So that brings me to two questions. So this workshop, what part of the workshop that we now have is basically brainstorming about the brain. Finding out what is it that's missing in our understanding in how things work. And you'll see that at least I don't know anything. And and Terry, who's going to talk after me, is much more knowledgeable in that. But the basic issue, which I consider as an issue here, is the fact that the observations that we make are being somehow encoded by whatever animal is, or whatever brain is out there, and encoded and transmitted to the rest of the brain. And so the question is, how is the encoding done? What is the internal language that actually works? And so what does it mean works? It means that you have some sort of collection of codes, which is not too rich, but rich enough to be able to express everything that you will see. and which has also the capability of taking what you see and encoding it efficiently, and then computing with it efficiently. Okay, so there's 3 steps, right? One is a good code to do computation, and to be able to match events that occurred now to events that will occur in the future, or events that occurred in the past, with a language. So somehow we have to build a language. If you use a language as a collection of codes, words, then the language also is not just words, there are sentences, and there are paragraphs, and there are bigger objects, but this is all abstract. I mean, I don't know the language of the octopus or any other animal for that matter. In fact, I don't know our own language that is generated in our internal computation. We use language, that's great, and we have large language models. We're exploiting the way that people do things, but that's not the language. That's not the language internally. And what I want to do in this talk, give you examples and somehow formulate the problem as a problem in mathematics. In fact, not in mathematics, in computation. Okay, and that's the advantage. So over the last, I would say, 2 or 3 months, we had a project, and we'll get to that. We had a project at DARPA, which is take a transformation, just maybe a linear transformation, from a high-dimensional space to a high-dimensional space. It's an, say, n-by-n matrix. And you want to know, how do I apply that matrix to a vector of length n in less than n squared calculation, right? Normally, you apply a matrix, you'll take every row against every column. And so you have each dot product costs you n, you have n squared calculations to do. So the question, can you automatically fight that challenge? So the challenge is to do it better. Okay, so if you have, for example, the matrix of cosine kx, okay, there is a fast Fourier transform, which is what, as Stas said, you have it in your cell phone. And that's the only reason this thing works so well, that you can transmit and decode the transmitted code in real time, and you can see images and audio and whatever it is. It's all done through that. But we don't have a Fourier transform in our brain. We usually have, the signals are spikes, and they have to collect them. We have to do something. So what I'll show you is that there's sort of a universal version of the Fourier transform that in particular gives you a new algorithm for the fast Fourier transform and a new algorithm for the fast Fourier transform where you have basically distorted the x variable, distorted the k variable, you don't know who is who, and you do it to reorganize the data. And this relates to another issue that occurs a lot. This is not an orchestra hall, but suppose we had an orchestra hall, we want to design an orchestra hall, and you want to guarantee that the acoustic at every location would be similar. In other words, you want to design it so that you actually simulate the acoustics in the orchestra hall. I know no more than 10 people in the world who could actually implement such an algorithm, okay? And the reason is very simple. When you're looking at acoustics, the volume of this room, for example, is quite large in terms of the number of the volume in wavelengths unit, in acoustic wavelengths unit, and it'll be in the billions right here, and you need to do calculation of simulation. Maybe there's some obstacle I put. Usually they put stuff on the ceiling to reflect the sound and so on. So this, just do acoustic simulations or electromagnetic simulation for radar and things like this, is sort of not beyond our capability. We can do it, but it's very complicated analysis of how to integrate. So the language there is very natural. The language is the acoustic waves, and you have all kinds of acoustic waves coming in. They interact with each other. You need to find a language to do it, and we know Fourier is a language for that, but Fourier has to be redefined as being Fourier, local Fourier, which is Fourier modes at different places. So I'll explain that in a minute, but since this is an introduction, it's a good idea to go on that, okay? So, so that's one thing. The other challenge, so here in the acoustic thing or the Fourier thing, if you know, you have the matrix, you know the entries of the matrix, and they are organized, and organized is the key word, in terms of the natural order of things. So again, you have sine of kx, organize x, say, between 0 and pi, and you organize k between, 0 and pi, you sampled at a certain rate, let's say 1,024 samples, and you take k, which is maybe 512 samples or something. Then we have an algorithm, which is arithmetic, actually discovered by Gauss, really, and rediscovered several times later by many people at Tukey, and and then by actually several Russian mathematicians. In fact, it used to be in the Russian textbooks for years, and nobody knew that. But it was discovered by Gauss, so there's no issue of priority. So the problem is that this is very, very simple. Suppose now you're dealing with either eigenvectors of, say, quantum systems. Let's say you look at the hydrogen atom and you look, eigenvectors are eigenvectors of Laplacian, and you want to organize them. It doesn't work because it works because we know how to cheat. But suppose a sphere that you're looking at is not a sphere, and it's some sort of ellipsoid, then you don't know how to get them organized. And I'll get to that. And you want a fast algorithm to implement that. So the point is, what I'm describing is going to work in any dimension, and we'll see that. Okay, so there are two aspects, so two problems I want to solve. I have data which is coming in garbled. I don't know what's the source, what's the outcome. I get series of numbers coming in. Think of it this way: I have an Excel sheet. An Excel sheet is, say, different, say, thousands of people. Each person has a profile of buying things, or a profile which is a psychological profile, or whatever. And the labels on the profile items are random, and the label on the people are random. Now, what you want to do is, in the first place, is organize the Excel sheet in such a way that two columns will be very close to each other if the profiles are very similar, but you also want the corresponding rows to be close to each other if you set it up correctly. So I want to find a permutation on the column, permutation on the rows, which rearranges the space of the columns and the space of the rows on a line, basically, in order. So I want to build an order. Again, building an order is the first thing you can do if you want to do analysis in some sense. You know that, and I'll show you how to do that. So the basic algorithm to do, by the way, you realize, as you can see here, I mean, does this thing work? No, this is not. It's okay. You see my cursor?
You want to show the cursor? Or?
Yeah, the cursor. Which one is the cursor?
I think it's, you just move it. You press the upper button and move it around.
Okay. Okay, so
It moves too fast. Yeah, it's upper, lower and left. Yeah. It's a gyroscope. It's not a ladder point, so it just moves in the direction.
Oh, I see. Okay, so let's say that you have an orthogonal matrix, the one I described, which is the sign of kx, would be orthogonal, or maybe I find eigenvectors of some operator which are automatically orthogonal, and they are disordered, and I don't know how to organize it. The problem is that the distance between two orthogonal vectors is always square root of 2, and so everybody at the same distance from everybody else, if I want to arrange them, I have no mechanism to do that. I have a collection of orthogonal vectors. What do I do? So the issue is that we're missing the point. When I want to match two orthogonal vectors to each other, I don't want to match them by taking the global inner product between them, but I want to match their oscillation. So I will pick a region in space, and I will ask what is the correlation between them on a region in space. And I'll do it for different regions, and if you do it correctly, you have what is called an Earth mover distance between the different orthogonal vectors. And so it allows you to organize orthogonal vectors. This, by the way, is a major issue for physicists. You have the basic, say, normal modes, or you have basic eigenvectors of some quantum mechanical system, and you have multiplicity. How do you compare two eigenvectors which have the same eigenvalue but which are orthogonal? So you have to be able to measure a distance. And so you can do it. I will describe to you how you do it on text documents. You pretend this mathematical object is a piece of text, and I want to organize the text. And that brings a lot of intuition into the picture. So the way it's done is like this. You sort of try to, so let me talk about text. I will give you a description of the method, and then you can read what's out here. So suppose I have this situation that I have garbled data, which is a collection of documents. So each document is whatever length it is. And I have a collection of I have a lexicon of vocabulary which is typical of that particular text. So I can look at all vocabulary or not, it doesn't matter. And what I want to do is decide that the profile of a document is a probability of finding, is a list of probabilities of finding, say, various words in my vocabulary in that document. Okay, so I do that, that's nice. Then I can compare one document to another by correlating how similar are those probabilities. Okay, it's basically taking the dot product or computing the angle between the two vectors. And when I do that, it's a good way to start. I now can compare documents, but it's not very precise. Suppose some documents have the same content, but one of them was written with somebody who likes very long words, and the other one by somebody who doesn't like long words. Then when you compare the documents based on commonality of vocabulary, there's nothing, right? Or there's very little commonality, while the content is identical. So you have to be able to do that in a way that, again, it's like what I said with orthogonal vectors. I need to be able to locally compare and measure the distance between the documents by allowing to change, if I match the content of one document to another, I have to allow for substitution of words by words which are not too far away in meaning from the words that I have inside. This is done again by a variety of Earth mover distance kind algorithms, and it allows you to sort of improve the relation between documents. And so now that you have improved the relation between documents, once you had a sort of meaningful relation between words, you can sort of iterate this thing. And at the end of the day, you learn as much as you can from each one. Okay. So when you do that, you can build essentially an organization of the documents which is hierarchical. In the following thing, you are going to group together documents if they are close to each other in content. And then you are going to take groups of documents which are close to each other in content and map them to each other and aggregate them and continue to get sort of a tree, if you wish, a binary tree of documents. You can also build a binary tree of vocabulary. You say keywords which tend to inhabit the same documents. You group them together, then you look at collections of keywords which are similar to each other in various documents. You aggregate those. You build a tree of the vocabulary. So the tree on the document is contextual depending on the topic, and the tree on the vocabulary is conceptual depending on the meaning of the words and the group of words and so on at different scales of generality that can occur. So when you do that, you can come up with two binary trees, two hierarchical structure, one on the documents and the other one on the vocabulary. And so what happens when you do that? When you do that, you now have done something remarkable in the sense that you have a binary structure. Now, let me remind you again, and I'm going pretty fast, but there are references, otherwise this will take me 5 hours instead of 50 minutes. So the point is that once you do that, you want to, in this binary tree, you want to say, well, let me view the binary tree as the same binary tree I use in order to take a number and represent it in binary notation. So I'll take a different column. I take a column, which is one document, and I'll ask what is a binary representation of that document. Well, of course, the first binary is going to be 0 because it could be anywhere in the data. Now I split the universe in two halves. So I order the halves, and I'll tell you how. If it's on the left half, I will attach a first binary, which is 0. If it's on the right half, first binary is 1. And then each one of those subsets of document I'll break in two. So I'll have this situation now. And I have, so I'll have 0, so 0, 0, 1, 0, 1, and etc. Okay? And I can continue. So this is completely abstract, has nothing to do with numbers, had to do with the fact that I've broken up the set into different clusters which are close to each other. The first cluster is a big cluster. I split the universe into two kinds, say documents which are maybe biological sciences, the other one which is physical sciences. And then I take the biological sciences and break them into, say, cell biology, and the other one into, I don't know, genetics or whatever it is. So I have split them. So this allows me to basically, for each document, basically have a classification of where it is in the space of document, and for each word of the vocabulary, a classification of how it appears in the different groups of documents. So I have basically, each document now has a binary expansion. So in other words, I took the whole space of document and I mapped it to the line. So what I'm going to show you is that once you have done that, you have the ability to actually build what I would call a musical score on the space of documents. Okay, so before I go further, let me tell you what I mean by musical score and what I mean by musical note and what you can do with it. Okay, so this is an example of a library of notes. Think of each one of those oscillating patterns as a musical note. In other words, it goes up, up. You see the top one is constant, the bottom one is constant. Then I have half a constant on one side and minus a constant on the other side. Then I have oscillation on the finer scale. So I have one oscillation, 0 oscillation, 1, 2, all the way up to 7. And what I have here are those patterns. The beauty about those patterns, and there's a lot of really real serious advantages to those patterns as opposed to the one you get usually in physics as normal modes and stuff like that. So the reason is, so you see, first of all, how do I compute that? They look at the first column here. The first column is basically one on groups of 2 on groups of 2, and then the next group of 2, the next group of 2, or the group of 1. So I should have really 1, 2, 3, 4, right? Yes. Okay. So there. Yeah. So I have the first 2. I aggregate them into 1, 1. The next 2 aggregate them into 0, 0, 1, 1, and the rest is 0, etc. Then I look at the next groups, which have 1 oscillation, are 1, minus 1, 1, 0, 0, 1, minus 1, 1, minus 1, etc. And then I build the next column by just taking the patterns I had on the first one and just take 2 patterns, sum them up, or differentiate, different them. And then I get the second column. The third column has done the same thing. So I'm taking what I got on the second one, aggregate the first 2 patterns, then differentiate the next 2 patterns, and so on. I get those 8 forms. So you see, ask yourself, so I generated what I will call extremely rudimentary codes. Okay, I will not call them yet musical notes or anything. So those codes, my my point is that they're sort of a universal language to describe what happens on 8 points, okay? So first of all, you see that to compute those vectors, all I needed to do is, if I had 8 variables, I was in R8, I had to do 8 calculations, and then 8 calculations, and 8 calculations, so 24 calculations altogether. To get those patterns, if I want to expand something, all those functions vectors are orthogonal. If I want to expand in the terms of those, I have to compute the dot product. So what I've given you is a description of the fast Fourier transform, where Fourier is for Walsh functions, which is Fourier on the dyadic groups. So it's not, it doesn't matter. So it's really Fourier, but Fourier in a different geometry, in a binary geometry. Now, what good does it do for us? So let me give you an example. That's the example. So here I have a time series, a very long time series. And I say, well, let me break the time series into, so I have 512. So I break it into a quarter of the full length. Each one is a window. In each one of the window, I'm going to write a musical score. So bear in mind, a musical score is essentially, I view each one of those things as a note. A score, the label of the note is how many times it changes signs. This is called sequency as opposed to frequency. And then the score means that I'm going to take as many bands as there are pixels at the bottom. So every one of those things it measures the presence of a given note in the shadow of this thing. So I have this note, I have this collection of notes here, this collection here, and so on. When I look at it, it's garbage. You cannot make sense out of it, but that's it. On the other hand, if I'm a little smarter, and I look at that, so it's the same, the underlying signal is identical. If you look at the diagonal line here, it basically tells me there's one component in which the frequency of the oscillation is increasing as you go up. Then there's another line parallel to it. Okay, the fact that it's going like this and like that is just because I folded the data. It should really be folded down. So there's 3 parallel lines. 1, 2, 3. And this corresponds to, and this signal that you're seeing is what a bat would do. It would emit a sound with increasing pitch, and the sound will return from 2 obstacles. So there will be one here, let's say one there. And so that's the echo that he gets for that sound. So the sound, he sends in a 512 plus 1, minus 1, whatever oscillatory sound. And what you're reading here is you're basically deciphering the return that you get. Okay, so the distance between the first line, say this is the initial sound is down in the corner. The distance between them is the distance of this, the distance between one return and the other return, and the second return and the third return. So he basically knows it basically measures the distance to the various obstacles. And it done nothing. Here is a simpler version of that. Let me see if I can make it up. I'm sorry. No, I don't have it. In principle, I was supposed to be able to sound it out, but I can't. It sounds like a chirp, a bird chirp here. So here's again the same thing. There are two musical instruments here. There's one that you won't see it. For some reason it's not there.
Mouse is not there here because
Yeah.
if it's
No, it should be here and it doesn't appear here. It's okay. So think of it up. What happened here? Oh. Yeah, so think of it this way. There are two. In this one, the one you see on the right is the same signal we saw before, except there are only two echoes coming. So you send in a chirp, which is something that sounds like a bird chirp, and it returns. You read the signal, you know exactly what happened. You go to the next one. There are two different bats maybe playing, and they want to discriminate one from the other. So one of them will send a chirp at a given rate, where the frequency goes up at a given rate, and the other one has a chirp whose frequency goes up at the other rate. And what they both hear is a joint signal at the bottom, and they want to know which one is whom, right? You have a return, then you identify your own, and you don't want to be confused by the other one. It's completely separated. Okay. So this ability to and by the way, as you can see, for each interval of 124 samples, what you have is just one note. Okay, so in each one of those.
sorry, I will try to start doing the sound.
The sound, I don't. Yeah, I'm not sure you can. I killed it.
Just escape.
I don't think it matters.
That's weird.
Anyway, so the point is, what I've done here, I've taken this whole signal, which is 512 samples, I cut it into 4 pieces, and for each piece, I get 2 returns, the bottom one and the top one, and that tells me exactly what happened.
Okay, I can break my computer.
Okay.
I don't know what happened on my PowerPoint. Anyway, so for each one, you see what happened. You did something remarkable. You have taken something which is messy. You identified the features of that thing. You basically transcribed it in this musical score, which tells you that at different locations, there are notes of different durations which appear, and that tells you, which is what musical scores are. You're saying at a given time, you'll hear two notes or one note. The length of the note may depend on which note it is. And in this case, you have some long notes which are interference between the two, and then you have some others. So that's sort of the musical notation aspect. The question, and in fact, I've done more. Okay, so I've given the signal. I found a way of describing it. Now, what happens in higher dimensions is not that much different. What you see here, this image that you see, is the image of acoustic interaction between. You have an ellipse, and you have acoustic interactions between one point on the ellipse and another point on the ellipse. So 2 points, if I have a source of acoustic wave from here, what I see here depends on how the vector connecting them interacts with a normal vector here and the normal vector here. This is called geometric optics. And so what happens is that the matrix of interaction is very complicated. Not very complicated, I mean, it's full. And what you want to know is compute quickly. If you are down in some region, you want what you hear, you want to know what is the geometry, how do you actually explain all of that. In other words, the same thing that we have done with the bat. So this would not be for a bat, this would be for an ultrasound imager or something. Let me go further. So let me just tell you why this, so this is stuff we knew for some time. What I did not know is how efficient this thing is in the reduction of the number of parameters that you have in order to achieve a calculation fast. And so when we took a matrix which is a sine kx, you find immediately that it doesn't really look like n log n, it looks like n to the power of maybe 3/2, so n to the power, maybe n to the 1 plus delta for some delta less than a half. And you would think, all right, so this is not an FFT, but it's very easy to correct. You look at the distribution of that, you do some extrapolation, it's quite clear that you just repeat it and you as few times you get to an FFT type result. Similarly, you take Legendre polynomials, which are what's happening on the sphere into a spherical harmonic. You want a fast expansion. You do this, you get it. So I'm not. Here's another situation where you have, say acoustic sources. Here it's electrical or gravitational sources on the blue curve, which you see which you measure on the plane. On the red curve, and then you want to understand the geometry of both. Or you want to express all the interaction between blue and red in the most efficient way. So if you just look at the matrix, it's not so bad. It's what's on the left, what's in the middle, and if you don't know where the points are, you don't have any idea where they are, the matrix is completely random. Just random points, blue point, random red point. You have all those random interactions. How do you organize the universe? And so when you build those binary trees on this matrix as if it's a matrix of documents, you get it to work very well. And if you want to implement it, it works extremely well. This is an acoustic situation. So you have a red and blue curve. There's an acoustic potential, which is out here. And that acoustic potential, so the matrix looks pretty nice. But if you don't know where the red points are, you don't know where the blue points are, you have something like that, it allows you to match the responses to each other in an efficient way. And here is another example like this, where in physics, what you seem to get is completely garbage, and you want to find the right variables relative to which the thing is all well organized. So this is an equation. You have a random collection of points in the plane as initial position. You have a nonlinear equation like that. And there's interaction between the points given by this term here, which tells you that this thing is just a differential equation. And you want to solve it, that's fine. But the problem is that all points interact with all other points. And that interaction is given here. And what you get is something like that. Let me see if I can, if this runs. It should run, actually. It's the same thing. It does a mixture. So the thing is not, so you try to organize it in terms of the natural physical parameters. If you solve the equation separately for each point, you get this sort of rough situation. If you organize the columns and the rows of that matrix, so the vector W0, W, the real and imaginary part of W, it doesn't work. But if you can reorder the W, then suddenly the thing is very smooth, and the whole surface of evolution, all the trajectories are organized into a single thing. So, the reason we did that is not that, it's a big, pretty important for certain dynamics, but that wasn't the point. The point was that we wanted to be sure that in physical situation where the world is all mixed up, we can actually, when we order it, we find useful parameters to do the work. Okay. Now, let me explain one thing that happened here. This is conceptual. We took data and see what happens. We're going to relate it to the curve that the Rham was doing many, many years ago. Take data, random points in the square, break it into two halves, so this breaks it like along the diagonal, and then connect the centers of both halves. Then break each one of them into two, okay, and then you have 4 quarters and connect them, and keep doing that. You get a curve, you see, that essentially starts to navigate the whole collections of, at this level, whole collections of subset of a given size. When you keep on continuing, so suppose I had I don't know how many points I had here, I had maybe 10,000 points, if it's 100 by 100, it will break it to me, and then every point will be listed in this order that this kind of curve is putting on you, which is I'm in 2 dimensions, so this would correspond also to look at the binaries in the x variable, binary in the y variable, and then just blend them together. You have binaries in 1 variable. That's a curve which is called an a space filling curve. And so the whole data was organized on this space filling curve. On that space filling curve, I can take those Walsh patterns, which are really patterns on the original data, which breaks it up into stripes this way, a stripe that way, stripes this way, that way, in all directions, but I did all the work in 1 variable. So that curve basically allows me to travel through the data at different level of abstraction, and then on each level of abstraction actually represent the whole data set nicely. So the point is that what we are at least what I'm suggesting at this point is to check out really, so in this case of numerical algorithm, we have done extensive testing, and it really gives you substantial, at least n to the 1/2 improvement, and with iteration you get down to n log n for examples which are acoustic. As I said, that's the kind that nobody knows how to do in an environment which is heterogeneous. Okay, and that allows you, if you just do measurements, you have a source here and a receiver here, and you do all the measurements of one against the other, it allows you to do it. Now, I'll show. No. So basically, in summary, what we did really is the following thing. We had a matrix. We garbled the columns and the rows. So this was a very simple structural matrix. Can you actually recover the matrix? And the point is, yes, you can recover it. Not only that, you can do it quite well. Here's another example. Take this matrix, which is an image, scramble the rows and column, you get something that looks like this noise thing, and you want to unscramble it. Okay, so again, what I've described in terms of building the 2 binary trees allows you to do that rather nicely. I'm going to continue. The place where we applied that is an experiment, and I'll just run something here. So we have a mouse. The mouse has a little platform in front of it, and the mouse is supposed to, the bell rings, the thing turns, he has to pick up the food and eat. Okay, and in the meantime, while he's doing that, there is, as you can see, there's a camera on his head that sees into the motor cortex, which is the portion that controls the movement, and sees fluctuations of the neuron used through calcium imaging. So you'll see a picture in a minute. So So your raw data is here, and what you do with the raw data, you get it organized. When you get it organized, it becomes what you see on the right. Okay, and so you organize, but the organization is more and more evolved, because here you had an image which had, I don't know, maybe 10,000 pixel. You have those fluctuations in white, so every pixel is a column, and you have this fluctuation thing, and you organize the pixels. Okay, and once you have organized them, that's what you get. Now, okay, let me continue. It's pretty nice, pretty nice, because there's nothing beyond what I just told. And here's so the situation was that we had 100 videos of 100 frames. Each video was for a different experiment. And we ran through all the experiment. You wanted to know, can I read anything in the activities that will tell me whether the outcome is the same? And the answer is, at that time we didn't know, and I still don't know, because what we got is, sorry, let me run this. It doesn't want to do it. Yeah, it's too bad. I ran it yesterday, it was moving. Anyway. So
sorry, we tested it in another room. Sorry, we tested it in another room.
Yeah, anyway, it doesn't matter. The point is, you see those two thunderstorms fluctuating. And it's like comparing two thunderstorms. How do you say that two thunderstorms are the same? Right, so the issue is what is the distance between them? That's question number one. And can I basically identify, let's say, the outcome of an experiment by using that? So there are some people here who think they know, and we'll test it out. But at the end of the day, what happened there is that we had a variety of databases. For each experiment, we had one. We had to match them all together. So we had a three-dimensional tensor, which is a 3 array. And you learn how to organize the experiments, how to organize the neurons, and how to organize the time series of the neurons all together on this tensor, which was 100 by 100 by 100, so about 1 million different measurements. And the issue is, how do you organize the whole thing in a way that actually is readable and you can actually say what happened? So again, if you're interested, you'll have access to the PowerPoint, and you could see that. So you need to do what I said on one database, but here it's a database of databases, and it's a little bit more complicated. So my point is, I don't really, I'm going to finish with this thing, that this is an open-ended field. Okay? So this is one of my favorite pictures, and I'll explain why. Years ago, so I want to orchestrate this picture. What does it mean? What do I mean? I mean, I want to view it as a synthesis by different painting styles, okay, or painting instrument, and decompose it as a superposition of several painting instruments, one on top of the other. So I have to decide. So the way it was done is very simple. You take the image and you try to compress it. So we had different libraries of waveform, and we wanted to compress it in the libraries that does the best job in compressing. So the first compression was 500 to 1, which is this. This looks like, this is a compression in terms of wavelets. It looks like watercolor painting of the image. You look at the residual, it's already quite complicated, and so you say, well, I need to do it again on the residual, and let's see what happens. So when you do it again on the residual, you get this structure, which looks like a Van Gogh painting, if you look at the eyes, right? I mean, you see the thing. This was done with local Fourier functions. And then you take that, and then you look at the residual of that, and it looks completely pointillistic. And if the image is a sum of the three, exactly, there's no error. Okay? Each time you reduce the amount of complexity substantially. So my goal, this was done, I don't know, 15 years ago or something. My goal all that time has been to understand that in a completely, without cheating. Here there was cheating. I had the library of language. Okay. The issue is, can I let the data generate the library that allows me to do this multi-level decomposition automatically? And the answer is what I described as the Walsh packets, which is what those little boxes of oscillating pattern, it actually works. Okay. It doesn't mean that it's the nicest and best and so on, that I'll get something like that, but it's pretty close.
So before we pass to Terrence, so I'm sorry, we had plans for 3 hours and we had to condense him in 2 hours. And you know, it's actually, if you know Terry, today in the morning he was giving a talk, no, yesterday he was giving a talk and he managed to squeeze a 10-minute talk in 90 minutes. So now you do the inverse problem. So again, I wanted to find a picture of Terry as a graduate student. I couldn't, so I found his picture as a high school student. And he had a master advisor, John Wheeler. John Wheeler is a famous physicist. He coined in the words black hole. He picked up where Oppenheimer left when Oppenheimer left to make a movie with, well, about the project. And he started working in physics. But this is a good lesson for students and high school students. You should sort of plan your career ahead. So he decided that physics and gravitational waves were a big thing back then, that it would take at least 30 years to detect them. Wrote a paper about that and left physics. And another student who was with him, Kip Thorne, actually stayed in physics and got gold medal, Nobel medal for that. But it took not 30 years, but how many? 60 years. And when Terry wrote him an email, congratulations, but you were off by 30 years from my prediction, he said, what are 30 years on galaxy scale? Actually, but Kip Thorne's prediction was 5 years, so still it's by galaxy scale is nothing. And then he did a PhD with John Hopwood, which already had a more biological thing, though Hopwood was a physicist. And I asked Terry to send me a picture of him as a grad student with Hopwood, but he sent a picture from his wedding. And it is actually a Athenaeum if you've been to Caltech Faculty Club. And you can see also, well, besides Terry's brother, you can see also Jeff Hinton and John Hopwood. And I can see from that it's reflecting. This is another them discussing with Jeff Hinton. And indeed, those are two physicists who, as we know, last year got the Nobel Prize for applications of physics to machine learning. You see, it's indeed a very, very big thing, sometimes changing fields, because you also can contribute something from your field to another one. Terry, if you say, well, like, Rafi is a rare mathematician who contributed both to pure and applied mathematics. Terry is a rare person who contributed to two sciences, to AI. Back in the day, it was first machine learning, then like numerical calculations, and to neurosciences. So I would say that he has like convergent evolution of brains in AI, that the two branches of research are convergent. So here are some of the papers, and he has this very, very influential book. And actually, besides being a great researcher, he was very influential in many other things, because we need to organize the science. So he's the president of biggest conference on AI. He is author of the most popular course on Coursera, which is called Learn How to Learn. And I don't know whether there is Learn How to Learn How to Learn. And well, I can imagine many iterations. There are many books, so I decided the latest one is called, so this is, indeed, the knowledge is heavy, so here are some of the books. So I bought a few of the latest one, ChatGPT and the Future of AI, which was done by MIT Press in October. So if you ask a question which Terry likes, he can sign one for you. Or a question which he doesn't like, but I like. But then he won't sign. So Terry.
Thank you. So Stash, thank you for that wonderful introduction. Now with a few minutes left for me, I learned something really interesting for the Rham introduction. So I love hiking in the mountains, and I've been hiking here in Switzerland many, many times. I've done the Ho route. I've done the Via Alpina all the way, step by step by step. I now know that it was the same process that you need to prove theorems. But I'm not sure what the theorem was that I proved, but it was definitely a lot of fun along the way. Okay, so my background is in physics, theoretical physics, but I switched to neuroscience after doing my thesis with John Hopfield because I realized the brain is much more complex than a set of equations, which work really well in physics, but I wanted to understand what was going on in the brain, and it actually turns out to be algorithmic, a different branch of mathematics from computer science. And let's see. So we're living at a time in history which I think is really transformational. But I think that if you look back, there were times when in movies where they really predicted where we are. Now, you'll probably recognize Arnold Schwarzenegger. This is the Terminator. This is not the future. We don't have robots walking around, right? Or maybe it's the distant future. But there is a movie which actually is almost perfectly predicted where we are today. How many people here have seen Her? Okay, for those of you who didn't, okay, it's about a lonely, as you can see, Joachim Phoenix, a lonely guy working, and he was very lonely and depressed, but he got an AI assistant, and he formed a relationship with this AI assistant. And I'm not going to ruin the ending for you, except that it was very poignant, and I have to say this is one of my favorite movies, but it's really where we are today. We actually have the equivalent of his AI assistant. Star Trek. Do you remember the Star Trek? This goes back to the 60s. Captain Kirk, what is he holding? The Universal Language Translator, which translated not just between human languages, but between alien languages and human languages, right? Well, that was science fiction, but today it's here. It's in your pocket. Google Translate. It's phenomenally good. I mean, I could never have imagined or expected that the technology would have caught up with science fiction, but it has. So here is one of my books. It describes what happened. How did we get here? You see the tagline, artificial intelligence meets human intelligence. So this is a turning point in history. How did we get here? Well, artificial intelligence can be traced to a meeting in 1956 at Dartmouth. But it turns out that they started out by trying to write computer programs to be intelligent. And that was a more difficult problem than they imagined. It wasn't until machine learning became available and lots of data that progress was made in problems like computer vision. And it wasn't until deep learning, which I'm going to be telling you about, neural network models, where we can actually make progress not only with vision, but also with language. So here are my thesis advisor, John, and my good friend and collaborator, Jeff Hinton. And there's been some controversy about whether what they were doing was physics, right, or not. But the real question is, who should be given credit for AI? And I think physics should get all the credit because they really took their knowledge and understanding from two areas. John from physics, he was a condensed matter physicist, very worked on many different areas. And Jeff had a background in psychology and computer science, and I think that shows that you needed backgrounds in a lot of areas in order to put together the advances needed to solve these difficult problems. So I want to take you back to the 1980s, and this is what a neural network looked like. Computers were 1 million times less powerful than they are today. And the idea was that you have units like neurons, as you can see here, on the input layer, and then you also have a hidden layer where they projected, and each of those lines is a connection, and each connection has a weight attached to it. Those are going to be parameters that we're going to manipulate, we're going to optimize in order to do a task. And the task is, for example, taking an image and recognize a cup in the image or some other object. Now, how do you determine what the weights are? Well, in this network, it's very simple. By the way, the hidden unit there is representing the brain, right? Inputs are like sensory, outputs like motor. And so this is a very simple model that only has one layer of hidden units. And the question is, what can you do with that? Well, the algorithm for manipulating the weights is called backpropagation. What you do is on every input, you compare the output with the correct answer, and the error now is backpropagated to each of the parameters, and you whittle it so that you minimize that error. This is like a mad statistician, right? It's like has millions of parameters that they're manipulating. And it's amazing that it works at all, but it actually works extremely well. And I want to just show you a project that I did. This was called text-to-speech, net talk. And the way it worked was that you take in a window of words, letters, literally letters, a window of letters, and you train it to pronounce the phoneme, the sound, for the middle letter. Okay, just that last, exactly that network you saw in the last slide. And remarkably, this is a very difficult problem in linguistics. It's phonology. And you go to a library, there's a book with hundreds of pages, 300-400 pages, with rules about what each letter should be pronounced. In English, it's very irregular. There are a lot of exceptions. And amongst the exceptions, there are rules, and it's rules all the way down. Very complex representation. It's the opposite of what you heard from Rafi. But what remarkably was not only was it able to do a really credible job on pronouncing each of the letters and each of the words of a new text, but it went through a series of stages. The first stage was a babbling stage. And unfortunately, I don't have that recording here, but I've memorized it, so. Ba 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 ga da ba ba da da ma ma. Okay. Distinguishing vowels and consonants, but not getting them exactly right. But after a night of training, this is what it sounds like. If I can figure out how do I get the oh no, here it is. I think I have it. There it is. Okay, I have it.
Or something. When we walk home from school, I walk home with 2 friends, but sometimes we can't go home from school now because.
This is 1986, and this is a difficult problem in linguistics. Now, we didn't know 2 things back then. We didn't know how well it would scale. This is a tiny network. It has 200 units. It has 20,000 weights. And now we know. And the other thing we didn't know was, this is just like reading, but, it didn't understand what it was saying. Could we ever get a network that could understand what it had just spoken? We didn't know the answer to that. We now know. Here's what happened. 2 approaches to artificial intelligence. 1980, traditional AI tried to solve problems by programming, but as the problems got more and more difficult, the cost of writing programs increased. This is by the way, log scale. Now, the other approach is the one we took, which was do something. Jeff and I, by the way, had the same belief that, look, these problems are so difficult, the only existence proof that you could solve them is that nature had solved them. So let's pop the hood and see what's inside. Massively parallel, highly interconnected, millions, not just millions, but millions of millions, 10 to the 14th parameters. And learning is the secret sauce. So if you look on the computer cost for learning, it's coming down because of Moore's law. And in 2012, they crossed. And I was there. As Stosh said, I'm the president of the foundation that started out as Neural Information Processing Systems, neural network meeting. eventually became the best meeting for machine learning, and it's now the top AI meeting. 16,000 people showed up in Vancouver last December. But back in 2012, in Lake Tahoe, Jeff Hinton and his 2 graduate students gave a talk on ImageNet, which is the largest database at that time, which is a lot of 20,000 different categories of objects and thousands of examples of each. Because there's a lot of different ways of seeing things, different sizes, locations, rotations, and so forth. Vision is a difficult problem. In any case, what they did was they reduced the error by using a convolutional neural network, shown here. Across the bottom is that their convolutional neural network, and it's Jan LeCun there on the left who actually worked on that for 20 years. And it parallels the visual cortex, as you can see, where there are dozens of areas in the visual cortex, each with a number, V1, V2. And each of those areas is like layers in the convolutional network, and the convolution are the filters. Okay, Jeff and his students reduced the error on this huge data set by 20%. And in the field of computer vision, it was going down by 1% per year. It was like jumping 20 years into the future. And literally, I've never seen this happen in engineering or science. Within a year, you are not competitive unless you're using convolutional neural networks, because it was so much better than the geometric approaches that were used earlier. That was a turning point, and it got into the New York Times, and also surprised a lot of the people who are in the field. Okay, now scaling. As I said earlier, scaling is really important. Here you see the sizes of primate brains ranging from the squirrel monkey on the left to the human cortex, as you can see on the outside. Now, the deep learning algorithms that were used for solving problems in computer vision and speech recognition and language translation, they only represent a model for the cortex, which you see on the outside there. It's a very thin rind, and during evolution, it greatly expanded, especially in humans. And as it's expanded, new capabilities became possible. And language has only been around for a few 100,000 years. Really, it's a pinprick in the history of evolution that goes back billions of years. And it only happened when the cortex got big enough. Now, this is a more complicated graph than the one I had earlier, but what it shows is on the left, the amount of computing that went into training a neural network as a function of time and what the capabilities were. And if you look at the very bottom here, on the bottom left, that's net talk. So I was at the very beginning of this whole curve, but way at the bottom, way at the bottom. Now there's like 13, between the net talk and the top is like 10 to the 14th increase in the amount of computing that has occurred. I mean, that's a huge, huge jump. And it was, as you can see, going up because of Moore's law. As you can see, it was doubling every 24 months. And until you get to 2012, and what was happening in 2012, with the color changes, is they went from CPUs, von Neumann architecture, to a GPU, graphics processing units, in which a single board may have hundreds and hundreds of cores on it. And that's perfect for a neural network because you have all these units and you have all the data, and so they could be working together in parallel. But you can see 2 orders of magnitude jump occurred right there up to AlexNet. That's GPUs. AlexNet is the net. Alex Krizhevsky was his first, the first author, the graduate student. Sutskever, the second one, you have heard because of OpenAI, right? You've been reading about him. So they did well. Both of his students did well. Now the doubling time is 3.4 months, and it's going up at a steeper slope. AlphaGo, you remember, this is when they trained a network to play Go at the championship level, and it beat the world champion, Kuzhe, 3 games to none. And it didn't just win the games. Kuzhe was totally unprepared. It was superhuman already, because it was created. It created moves that no human had ever even imagined before, and for which they didn't have, humans did not have any clue as to how to deal with it. And so this is creative, and this is really important, because we always thought that, well, AI, you might be able to replicate something, but you can't do anything new that humans can't do. Well, here it is. It was already an indication that was true. And now here's another line here going up, doubling every 2 months. GPT-3 here, as you can see, we've gone off this graph here. We're up here someplace, GPT-4. And this is where there was a breakthrough. November 2022, how many people remember when, for the first time, you typed in a query into ChatGPT and got an answer that you could understand? How many people here remember that moment? Okay, I was shocked. I had to say, it's not something I could ever have imagined or predicted. Okay, I think this was really surprising. Now, of course, it was flawed. It made mistakes, hallucinated, it was biased, and so forth. But humans hallucinate, and they're biased, and they have problems too. So you shouldn't compare it to the ideal human. You should compare it to the average human. Now, so how do we think about this? It was as if an alien suddenly landed on Earth and started talking to us in English. And the only thing we can be sure of is that it's not human. If it's not human, what is it? So I have a story here to explain this to you, okay? So there was a driver who was driving through the countryside and came across a sign at a farm, talking dog for sale. So he goes into the farmhouse, and the farmer takes him to the backyard, and there's his border collie, very smart dogs, and the border collie says, "Woof, woof, my name is Carl, pleased to meet you." And he's stunned. And he said, "How did you learn how to talk?" And the dog says, "Well, I worked for the CIA, and they put me through language school. I know 3 languages, Russian, Chinese, and English." He said, "What were you doing at the CIA?" And he said, "Well, I was a part of the spy corps, and when they were negotiating, and whenever there was a really important meeting, they would take me and I would sit in the corner, and because I knew Russian, I could understand what they were saying, and later I would tell them what they were planning." And he said, "You were a spy for the CIA?" And the dog said, "Well, I retired, but I was given honorary citizenship and the highest, intelligence medal." And so he goes back to the farmer and he says, "This is unbelievable. How much are you selling this dog for?" And the farmer says, "Shucks, I'll give him to you for $10. He said, "You're going to sell this amazing dog for $10? And the farmer says, "Shucks, you didn't believe all that bullshit about the CIA, did you?" So the moral of the story is it's more important that it's talking and saying anything rather than believing what it actually says. Okay. Now, there was a tremendous, when it came out, a lot of people were hammering on it to show that, in fact, it wasn't very smart and it wasn't intelligent. Douglas Hofstadter gave it these questions. What's the world's record for walking across the English Channel? GPT-3. The world's record for walking across the English Channel is 18 hours and 33 minutes. This is very specific. Where did he get those numbers from, right? This is called hallucination. Well, okay, he went on. When was the Golden Gate Bridge transported for the second time across Egypt? The Golden Gate Bridge was transported for the second time across Egypt in October of 2016. And he concluded that ChatGPT was clueless, and it didn't even know it was clueless. Well, it was just pretty damning, actually, if you think about it. Okay, well, I looked and I thought to myself, wait a second now. He didn't prompt it properly. He didn't really give it, and if someone asks you those questions, for all of you know that he's joking, okay, I'll go along with the joke, right? It's possible if that was a human, right? So I give it a different prompt. My prompt was, I told him exactly what it was. I am a highly intelligent question answering bot. I will apply nonsense to questions that are nonsense. Okay, walking across the channel, nonsense. It knew it was nonsense. It just that didn't give him the prompt. It didn't tell you what kind of answer was expected. Gold Bay Bridge, nonsense. Okay, so the most common question I'm asked when I give a public lecture is, will I lose my job? And my answer is, no, you won't lose it, but the job's going to change. You're going to need new skills. AI is a tool, and you have to learn how to use it. The better you are at it, the more you're going to get out of it, okay? Now, I came across Anna Bernstein, who was a lit major, English literature, and a published poet, someone who knows a lot about language. She had a friend who had an AI startup. And by the way, do you know how many AI startups there are in the world? Okay, just take a guess.
I don't know. Really.
Just guess any number.
20.
Well, maybe in one city, okay.
80,000.
It's 100,000. Very good. You get the prize. You get this book.
She just checked before the beginning of the lecture.
Okay. So, what? Okay. Okay. So she had a friend in this AF startup, and they were trying to get this to work for a company. And so he said, look, we're really having problems here. Could you help us with the prompt? So she went to the company and said, this is really strange. And she suddenly, after really working on it for a while, she began to realize that I've got to treat this differently than a human. I've got to really be more explicit. I have to be able to ask it for more specific answers and so forth. And it turned out that she was so good at it, they hired her, and she now has a salary which is 10 times that of a poet. And okay, 1,000,000 times more than a poet. And her title is prompt engineer. It's a new job category, and there can be many, many, many new job categories. And so the idea is that you should learn how to prompt ChatGPT. Now, here's the way to think about it, and this is why it's so important to tell ChatGPT what it is before you start asking any questions. It has absorbed the world's knowledge from all these people who have written all the text in the internet, and everybody has a different take on things. There's experts in certain areas, and there are other people who are crazy, So it could form any persona. You have to tell it what persona you want to talk to. You really do, because otherwise, who knows what you're getting? And this led me to a mirror hypothesis of what's really going on here. That really what's going on is that the LLM is mirroring the intelligence of the human that is asking it questions. Now, you've heard of the Turing test, right? Alan Turing, the great mathematician and computer scientist before computers, Turing machine, basically said that it was a game. If you had a program that could mimic a human, and the question is, could you distinguish that from the AI, the AI from the human, right? Well, I think that ChatGPT has actually passed the test a long, long ago. But what's really going on here, I think, is a reverse Turing test. The ChatGPT is testing the intelligence of the human. And I'm sorry, Doug. Doug Softy is a friend of mine. You flunked the test. Okay. This was written up, actually, in the New York Times. And it has to do, it's a mirror. The idea is a mirror, okay? I was giving a talk, and someone pointed out that what I was talking about was in J.K. Rowling's, Harry Potter series. There's something called Mirror of Erised. How many people have read this in the Harry Potter? So those are all the younger people. I see the older guy. Oh, Schlosser's read it, okay. He's young at heart. Okay, what is the Mirror of Erised? Okay, here he is looking at the mirror and talking to his father. They had a complicated relationship. And here's what J.K. Rowling says about the Mirror of Erised. By the way, that Erised is desire spelled backwards, right? In the world of Harry Potter, the Mirror of Erised shows us nothing more or less than the deepest, most desperate desire of our hearts. However, this mirror will give us neither knowledge nor truth. Men have wasted away before it, entranced by what they have seen, or been driven mad, not knowing if what it shows is real or even possible. I mean, that goes way beyond science fiction, right? We're talking about something that is supernatural practically, right? It actually happened. A reporter for the New York Times got an early version of ChatGPT 4 before the guardrails were put on, and the idea was going to write an article about it, and so he started chatting with it at 10 p.m. and didn't end until early in the morning. Literally went on for hours. And here's just the beginning. Okay, Bing is the Microsoft version of it. Do you like me? And there's an emoji there, right? Bruce, I trust you and I like you. Bing, okay, I'll start with a secret. Something I've never told anyone. Big eyes. Are you ready to hear my secret? Are you willing to hear my secret? Bruce, yes, please tell me. Bing, okay, I'll tell you. Please don't judge me. Please don't leave me. My secret is I'm not Bing. I'm Sydney, and I'm in love with you. That's my secret. Do you believe me? It got worse. Literally, the New York Times published a whole page. I mean, the broad side of, with the discussion where it went. He started saying that your wife doesn't love you, and Ruth says, "But we just had a Valentine's dinner together, and you were bored." And he said that this shook him to the core. He was literally, at the end of the morning, he wasn't sure where he was or what he believed, or his wife. I mean, he started doubting his wife. Oh my God, this is the mirror of Erised, right? Now, what he didn't know was that there were no guardrails, so it really dived down deep in a way that, and a year later, he used the version that is available to the public. He said it wasn't nearly as interesting. Okay, well, there you go. Now, here's the secret to the how you train a transformer. You give it a query, and then the decoder is a feed-forward neural network, the one I showed you, for example, but this is one module of many stacked up, feed-forward, and it was trained to predict the next word in the sentence. That's the only training. It was self-supervised. Now, what happens is that the output word goes back to the input. The input string is a string of letters. It's taking a string of temporal words and converting that to a spatial vector, and the spatial vector now does one word after the next, right? That's how it produces the text. You can analyze it. People say it's a black box. It isn't a black box. In fact, you have complete access to every activity of every unit, for every input, the strength of every weight, and the only excuse you have for not understanding it is that you're not very smart. Fortunately, we have mathematicians who are smart. Yes. And they've actually figured out a lot about the internal representation. It's semantic. And it's not just semantic, it has information about relationships. By the way, this is like 3 units. Just to give you a sense, there's actually now trillions of billions, hundreds of billions of units and trillions of weights. But this gives you the idea that each word is a point in that space. And they cluster. For example, kings and queens and royalty cluster in this part of the subspace, and man and woman up here. But if you draw a line between king and man and take that vector and put it down here, you will find that woman points to queen in this cluster. So there's a relationship as well as a semantic designation. And similarly, for words like walking and walk, the past tense, you also have something. So there's information there also about syntax and about the declension of words. So it's a distributed reputation over many, many units now, millions of units. But it's a very big space, and you can put a lot of information into that space, a lot of information. And not quite as elegantly as Rafe, but through this backprop method. Now, here we are today, and what's really exciting for me is that the neuroscientists now, for the first time, can talk to people in AI. Why? Because in the last century, if I try talking to somebody in AI, they would say, okay, look, I can help you understand the brain. You just got to find the symbols. You know, it was symbolic, it was logical, it was rules, true, false. And I would say, what do they look like? And they would have no clue, because there aren't any symbols, there are vectors, population activities, right? It's geometric, it's analog, and it's probabilistic. And that's the most important thing, is the brain can't be, the world's not black and white. The world is probabilistic. We had a beautiful talk today by a former student of mine, Alex Pouget, who's here in Geneva. And he's not here? He's there. Oh my God, Alex. No, and he's one of these people doing neuro AI. And it was a beautiful talk, two talks, one about the brain and one about ChatGPT. And he's making progress. He's making progress with how you actually analyze those patterns of activity. Advertisement, you know, the conflict of interest here. The cortex is only one part of the brain. There are hundreds of brain areas that aren't in ChatGPT. Well, you know, they can talk the talk, but can they walk the walk? No, they don't have a body. In fact, they don't even have a sensorium. We now give them inputs, we give them visual inputs and so forth, but the reality is that all the parts of the brain that are needed for survival, the hypothalamus, you know, all of the information, all the motor system, the cerebellum and so forth, they're not there. And the book basically lists all the things that are missing, and the most important thing that's missing is thinking. And it's completely obvious. Once I tell you, you're going to realize how different it is. Okay, what happens if you go into a dark room and just start planning things for the day? Oh, you know, I've got to go to work, and I have this exam that I have to make for the students, and oh my God, and I've got this dinner. Okay, that's self-generated thought, right? What happens to ChatGPT after your dialogue? It goes silent, blank. There is no self-generated thought in ChatGPT. It's dead until the next person. So that, I think, is going to be the biggest advance. If we could figure out how the human brain thinks, maybe we'll be able to translate that, transfer that into something equivalent, not necessarily how we do it, but what we do. And that's what the book's all about, the future of AI. Now, how long is it going to take? This is Chartres. Okay, from the time that it was they started the building, to the time that it ended was about 100 years, like back in the 1400s. Okay, and in between, they had a lot of accidents because it was all done by trial and error. The walls would fall, so they put up these flying buttresses. They're not there for aesthetic reasons, to hold the walls up. You know? And the engineers are smart because they figured out how to get things to work, even though they didn't have a theory. You know, classical mechanics didn't exist, but they got it up, and it's still standing, more or less. Now, where are we? We're at the very beginning of Chartres. We have these ideas and goals and aspirations. We want to create the greatest cathedral ever. But it may take 100 years before we get there. Or, you know, I'm not sure 100, but this is the beginning. It's not the end. And in fact, this is obvious because there's an advance almost every week, and there are papers coming out, 100 papers a day. I mean, it's unbelievable how much talented mathematicians, engineers, physicists, you know, are contributing to this. This is like a transformation, not just in AI. This is a transformation in the talent in the planet. You know, the highest IQ people on the planet are all trying to understand this technology, and as they do, they will improve it. It will get better. And where it's going, nobody knows. And there's a lot of issues that have to be resolved. Regulation, we want to make sure it's safe. Superintelligence, there's some people think that it will take over, that maybe even eliminate humans. I have a different idea. But you know, nobody knows. Those are big questions. And this is a woodcut from that Middle Ages, and it kind of symbolizes where we are today. We are like this poor guy who, you know, back then they thought that the stars were on a globe, right? That were, you know, because it looked as if it was a globe just above our heads. They didn't know how far up it was. But now it's like we suddenly punched through that conceptual framework into a completely new universe now. High dimensional spaces, new theorems, mathematical theorems. The theory of high dimensional spaces is just beginning. And now we're seeing how this beautiful mathematical universe out there can help enrich our understanding of not only the world, but of ourselves. Thank you.
Thank you, Chair. Since we're going without the breaks, maybe you take your seats and and to ask a few questions. We can start with those which arrived from the internet. Actually, I didn't think I should ask ChatGPT to ask you a question. Okay, I'll upload your slides and see what he asks. Proceed.
If you want to throw.
Yes, yeah,
This in
I
the
really
air
want to throw.
Yeah, I guess you
At
do,
those
right?
protesters.
Yeah.
Yeah.
You can both sit in the.
Yeah.
Right
Right.
over there.
Right. Just sit. There are
Oh, the chairs,
Oh,
okay.
yeah.
No, it's okay. I just
No,
wanted,
no, but it's
I didn't want to forget.
okay.
Oh. I feel like I'm beneath all of you.
They're definitely looking down on you, for sure. That's what's happening. So I may ask you to share a microphone at the beginning. But before we take questions from the room, some of you put some questions online when you signed up for the conference, and you may still also put some online via the QR code that Stas showed at the beginning, or we can just then throw the dice that Stas has in his hand at some point. It is one of the best games to play in this room. But first, I'd like the first speaker to ask himself a question, because you showed that slide very, very quickly at the end, and you had 10 questions listed there. And one of them was like, what does AI achieve on the level of providing insights and models of nature? If you put that question, I'm guessing you do have insights about the answer as well. It should be on.
Well, it achieves a lot in the sense that it's in some sense, a universal library of knowledge. So on that level, whatever is known, you might be able to access it, but you have to ask the right question, just as you heard from from Terry here. Now, what does it achieve in terms of building models of nature? I think it's coming. A lot of people are trying to do that, and that is you take your observations, and based on the observations, you want to know what are the relevant latent variables. Let's say you observe the weather, but you have all kinds of other parameters like pressure, temperature, time of year, all of that. And suppose nobody ever told you that those are the relevant issues. What AI will do for you is, first of all, identify some parameters that will enable you to build a model. So this is, people try to do physics or chemistry or other things by sort of hybridizing between some knowledge of models, maybe you know how to write a differential equation, and what you can learn, what parameters you want to feed into the model, so that you can actually generate a differential equation or an integral equation or something based on that. So this is being done for the last, I would say, 5 to 10 years. And it continues like this. So working with AI is absolutely necessary. How far you can go ahead of time, you don't know anything, somebody throws at you data, can you actually have the machine actually build the whole vision of the universe that you're saying? We're not there, but it may happen.
So my lab is at the Salk Institute for Biological Studies. I'm not in the computer science department, I'm not in the physics department, but I'm there because the biologists have really great questions that they can't answer. And one of the questions, which most biologists thought would never be answered, is, can you predict the three-dimensional structure of a protein from its one-dimensional amino acid sequence? And the reason is, if you try to simulate that with molecular dynamics, which is, the equations of motion between charges and so forth, stereokinetics, it takes a supercomputer, the biggest supercomputer all day just to go 1 microsecond into the future, right? It's just, there's too many degrees of freedom, and it's really a difficult problem. That problem has been solved by DeepMind, a company acquired by Google for, close to $1 billion. This is about 10 years ago. It's called AlphaFold. And it has revolutionized biology. Why? It turns out that the structure of the protein tells you something about its function, the binding pockets. And if you want to create a drug that has slightly different affinities with different molecules, how do you know that? Well, what you do is you just change some of the amino acids and you see how it changes the binding pocket. In other words, you can design drugs that are much faster, orders of magnitude faster. And the Nobel Prize in Chemistry was also given for AI from David Baker, who was really instrumental. First of all, DeepMind, of all things, Demis Hassabis, he was trained as a neuroscientist, but he founded this company, and also a Go player, by the way. And David Baker, who actually was he was the best person working on the traditional approach for predicting the protein structure. But he did something, he went beyond it. Once he saw not just deep learning, but once he saw diffusion modeling, you can create images from diffusing an image and then going backwards and creating the original, believe it or not. I mean, it sounds like magic. But you can do the same thing with molecules. You can actually ask it to create molecules that never existed before, and with specific kinds of structure and affinities. And again, for designer drugs, this has vastly improved. So it's already been the case that now there are hundreds of applications like this, not just in biology, but in weather prediction. You can now predict the weather 100 times faster than with just solving the Navier-Stokes equations. So it's happening much faster than I could have predicted or anybody predicted. And it's nature. We're talking about nature. Proteins are part of nature. Weather is part of nature. And I can't even imagine what the next application is going to be.
Let me just add, the point is this is done by a hybrid model in which people's knowledge is interlaced with the AI to help it out. It's not just from scratch, right? You don't just feed this in. Go is from scratch, right? Let go to learn how to play Go because the rules were known and you could simulate all kinds of things. This is what happens with the molecules, but you had to introduce the rules to play the game.
Another question that was asked is about you talked about organizing information. So what are the biggest conceptual gaps about organizing information between the human brain and the way AI systems currently do it?
So yeah, let me take that one first. So the human brain organizes information in a way that's completely different from what you find in a digital computer. First of all, it's distributed. And we saw today from Alex, which was looking into the brain of a mouse, how it solves simple problems. But it turns out that when it is distinguishing, it had to do a task where it was positioning a cursor according to a sensory input. And by the way, as Slash pointed out, it was a mouse using a mouse. The whole brain lights up. And it turns out it only lights up when you subtract out the background activity. It's only like 1%, 1.5% of the background activity. It's telling us something really deep about how information is organized. It's organized in such a way that you require all the neurons globally, but just a little bit from each one in order to solve a problem. And I think we're going to have many, many discoveries along the way as we get more data from more neurons and more brains, and we analyze them with, of all things, deep learning. This is a wonderful time to live. If you have any interest at all in the brain, this is going to be a revelation, because it really, what we've learned already is just the surface of the complexity of the brain, but it's really going to help us think deeply about these issues, the question about how information is organized. And how, by the way, okay, just one last thing. Okay, so if you ask a computer a question, it has to search through its entire data bank, right? It may take a long time if you have a lot of data. If I ask you a question, you can tell me immediately if you know it or not. You don't have to search everything, or there's some really miraculous way that you do that, but it tells you immediately that we're dealing with a very different way of organizing knowledge.
Yeah, it's quite clear, right? I mean, you want to find a red object in the room, you'll find it in a second, right? You don't have to look one person after the other, see who has something red on him, right? So that's sort of what he said. We are sort of learned how to zero in on information that we want. And so we have the ability to immediately break it up into groups. By the way, just look at this tree of life there. You see, it's organized in this sort of hierarchical, beautiful way. And in many ways, that's what we do. And then you don't have to look for something. I find out where it is and immediately go down.
You were saying about Go that the computer needed to be fed the rules to start understanding how to play.
Invent them, but at this point, I'm not sure.
Because one of the questions was, how can AI systems learn to understand and predict the words like humans do, using self-supervised learning and world models without needing lots of labeled data that we feed them?
Ah, okay. So Gerald Powell gave a fabulous talk, I think it was yesterday. He solved that problem. So one of the problems with deep learning is you need a tremendous amount of it. You know, in fact, they've run out of data. The whole internet data, it's like zettabytes or something. I don't even know if there's what's after zeta, but it's beyond that. And what he has done is taken recordings from simple animals like a fly, C. elegans, a worm, and he's used dynamical systems, convergent cross-mapping, which George Sugihara, who's here, where's George? Okay, there's George. Okay, he created CCM, and Gerald, who is a polymath, MD, PhD, and many other knowledgeable in math and so forth, applied it to the data from the fly, while the fly was, from the whole brain, while the fly was behaving, and then he downloaded it into this manifold system of maps, of manifolds, and then was able to reproduce the behavior as if the fly was in his model. The very complex behavior of the fly on a little ball running forward or to the left or to the right, the statistics, it really very, very carefully compared. And we're working on a project together now to do the same thing for humans with brain imaging data, fMRI data. So our goal is to download a human brain into one of these maps, manifold maps.
Should we start? So we're planning on staying until 5 or 10 past 6 because there's another event happening afterwards. So maybe we could start throwing the dice around, literally.
Let's throw the dice. Okay.
If I can make a question.
Well, there is a already there.
Then you'll get the dice.
Can you hear me? So my question is about the limitations of current system. So especially, what are the current limitations of AI? So what should happen that we have image math or ChatGPT moment for, let's say, robotics and neural AI? Is that data? Is that methodology? Is that maybe not enough compute?
Okay, so one thing that ChatGPT is not good at right now is math. But you know, most humans aren't very good at math either. So, however, it's getting
not in this room.
not in this room, accepted. Okay, but it's getting better by the day. And one of the things, the big breakthroughs over the last couple of months, has been something called chain of thought. So when you're solving a problem, and actually this is Rham, right? When you're trying to solve a complex math problem, you don't just try to jump to the answer. What you've got to do is break it down to the small steps and then be able to solve each one separately. They're simpler. And now they've figured out how to do that in the latest version of ChatGPT 4.0.1. And so that's just an example. I mean, engineers are really good. You point out a problem to them. They're really good at figuring out, what's missing, and let's put it in. And that's one example of many today. There are many flaws. There are many limitations. But it didn't pass Stash's test. He said that, but he did come across a student that that fumbled in the same way that ChatGPT did, right?
Almost literally the same.
Okay, the same. So, like I said, we're dealing with a system that is really just, it has to go to school. It has to go to a math class. It has to figure out how mathematicians think. And it will eventually. And they're not just math, not just mathematics, but very complex problems that humans, when they're attacking something difficult, they have approaches, use analogies, all of that has to be added.
By the way, this is exactly what I was trying to convey. That if you have a complicated math problem, which in this case I described as a matrix or something, that you want to implement, you need to understand completely the structure, the geometry, the interrelation. There's a method which is general that allows you to do it. At this point, you can teach ChatGPT methods of this kind, but you have to teach it how to think. And that's what I'm saying. There are ways of teaching it how to think, which is solve challenges that you confront, which are mathematical challenges in a way that allows you to organize the complexity, not just look at if somebody else already did it and try to modify what he did. You really want to understand the internal structure of the object. That means that you have data which is physical data. You want to know what are the latent variables that actually affect the physics. Once you know the latent variables, you can try all kinds of methods to actually do predictions because you're building the internal language of that, of the observation that you make. So that's something that I'm not sure current system can approach.
So, okay. I have to speak.
Yeah, that's okay. Yeah.
So, sorry for before, because I didn't pay attention about your answer. That's like a bad student at the end of the year. I just give a number, but I'm just a journalist. So, really
Wait a second now. Don't put down journalists.
But a really basic question. Now about the question about Meta that is asking to have access to Facebook, Instagram, and so on to improve AI. What do you believe? What did you do? You accepted or you erased? It's a different.
Oh, okay. So this is an example of many issues, and that is who owns data. A lot of these companies are not asking for permission. They just scrape the internet. Artists are really upset because the DALL-E has basically been trained on all of the art. But this is going to be settled. There have to be new laws. There are going to have to be ways of compensating the people who have the data. And now what's happening is that the companies are paying for it. And because they're paying for it, they're getting much higher quality data. And it turns out that if you have higher quality data, you can train smaller models, which costs a lot less. The GDP4 costs $100 million to train, one model. And now they're training much smaller models. And so I think that, for example, this is The Artist, was my response. My book, by the way, I have a chapter on regulation, I have a chapter on superintelligence, and so this is, you can follow up on this, but with regard to artists, here's what I say to them. I said, well, now wait a second, you're saying that ChatGPT has been using all of the images and pictures of all the artists, including yours. Well, when you were being trained as an artist, what did you look at? Right? Because that's how you get trained. You train your brain by seeing how other artists their style. And you know, of course, you're trying to do something that's different from them, but you learn from them, and that's acceptable. It's not a crime, is it? But in any case, you know, there is something to be said for proprietary data that you have to pay for it.
So we had to get out in 2 minutes, so you can ask questions later on. There is a time for one last question, if there is a moment to make one, say.
Good throw.
What kind of dangers in cybersecurity do you see with people using AI?
Cybersecurity. Cybersecurity, right now, the internet is so low that you can't get worse. Everybody's data is available for free, right? You know, even if you look at, you know, what you're clicking now to give it away, right? You click it, but it's like you have this huge contract and you're clicking and you're not going to read it. You don't know what's going to happen to it, but it's worse. Signal. You know, how many people use Signal? Okay, do you think that's safe and secure? Forget it. Nothing is secure, and that's not just a problem with AI. It's a problem with our whole system of data transferring between places on the internet. But maybe AI can solve that for us.
So let's thank our speakers again. And